Okay guys, so we would like to prove the Euler's identity, which is that e to the power of I times pi is equal to -1. So how are we supposed to do it? Well, first of all, a nice thing would be to prove the Euler's formula, which is that for every single, well, angle theta, which is an argument of a complex number, we get that e to the power of I times theta is equal to cosine of theta plus I multiplied by sine of theta, or sine of theta. Well, how are we supposed to prove it? I would like to actually use the Taylor series expansion for e to the power of x, which looks something like this. Yeah, so it states that e to the power of x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on and so forth up until infinity. Yeah, so we can actually go on and use this formula in order to rewrite this e to the power of I times theta pretty smoothly. So we can just say that is equal to, maybe I'm just gonna do it in pink. Yeah, so e to the I times theta is gonna be equal to, that's just gonna be 1 plus, well, I times theta, and then, well, I times theta all squared over 2 factorial, then is gonna be I times theta cubed over 3 factorial, I times theta to the power of 4 times 4 factorial, 1 over 4 factorial, and then 1 or I theta to the power of 5 over 5 factorial. I'm not good at writing something and talking at the same time. It's like I shouldn't be doing my videos. Anyway, so, well, now I think we could go on and simplify this thing a bit. So, for example, this I squared there is just gonna turn out into -1. This I cubed here is just gonna be a negative I. This I to the power of 4 here is just gonna be 1. This I to the power of 5 is just gonna be a positive I. So that's pretty lovely. We can just go on and write this entire thing as e to the I theta being equal to 1 plus I theta, and then minus theta squared over 2 factorial, and then it's gonna be minus I times theta cubed over 3 factorial, and there's gonna be plus theta to the power of 4 over 4 factorial, there's gonna be plus I theta to the power of 5 over 5 factorial, and all that stuff. I forgot to make the dot. I forgot to prolong this sum here, but it doesn't really matter now. Yeah. Okay, so, well, this sum should make you remember something. I mean, it should recall you something from Calc 2, and it is the power series. I mean, probably the Taylor series expansions for sine of x and cos of x. I mean, no, probably is those two expansions mixed up together, but probably you should recall them looking at it, but whatever. So, well, we know from Calc 2 that sine of x is equal to, x minus x to the power of 3 over 3 factorial plus x to the power of 5 over 5 factorial, and then minus x to the power of 7 over 7 factorial, and so on and so forth. We're just going to be extending this alternating sum up to infinity. And then, well, cosine of x, that's just the derivative of sine of x, so we can just kind of take the derivative of this stuff right over there, yes? So we will get that is equal to 1 minus x squared over 2 factorial plus x to the power of 4 over 4 factorial, and then minus x to the power of 6 over 6 factorial, and so on and so forth. And, well, it's pretty lovely because, or maybe, let me just kind of change colors here so you will be able to see more clearly what I'm doing here. I'm gonna change it, I don't know, to green. It's a nice color, yeah? So first of all, the sine of x Taylor expansion. You see, we've got an I theta here, and theta cubed there, a theta to the 5th over 5 factorial there. Okay, well, it starts to look like the sine of x expansion, and then here we've got also 1 theta squared over 2 and theta to the power 4 over 4 factorial, just as in the cosine of x expansion. So let's just kind of go on and group all the terms here into two separate sums. I'm gonna say that e to the I theta is actually equal to, and now I'm gonna use those colors, is gonna be equal to 1 minus theta squared all over 2 factorial plus theta to the power of 4 over 4 factorial, and you know, all that stuff all the way up to infinity. And then all the terms that have an I multiplied by them, yeah? And so, well, let me actually just go on and take out that I before I do the grouping, yeah? So I'm gonna take that I out, and I'm gonna get just the theta and then minus theta cubed over 3 factorial, and then plus theta to the power of 5 over 5 factorial, and then minus dot 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 all the way up to infinity. But well, once again, this thing right there is just it's just cosine of theta. And this thing here in yellow is just sine of theta. And so we can just pretty nicely say that this e to the power of I times theta is equal to cosine of theta plus I sine of theta. And well, why is it even a useful property to begin with? Well, if I were to draw myself the complex plane, yeah, so this is my complex plane, this is the imaginary axis, this is the real axis, and I would like to mark myself some kind of point. I'm gonna call this z is gonna be my complex number represented by a point in the complex plane. Yeah, it's gonna be equal to some a multiplied by, well, just a 1, so the real unit, plus b multiplied by the complex unit, which is I. So, well, we see that if I were to mark myself the distance that connects this point with the origin, this is going to be the absolute value of z, yeah? So the distance from z to the origin in the complex plane. And now if I were to mark myself the two distances, the vertical and the horizontal one, that when walked together will get me from the origin to that point z, well, I can actually pretty nicely get the formulas for those. I can evaluate those two lengths using this using this absolute value of z, so using this length from the origin to z, and also the angle theta, which is the angle formed by the real axis and the line segment that connects my origin to the point z, yeah? So we see that the length of this line segment here is just gonna be the absolute value of z cosine of theta, and the length of this segment there is just gonna be the absolute value of z sine theta. Well, that's awesome, because this means that I can rewrite my z being equal to a plus bi as just, well, a is how much I have to walk on the real axis, yes, so there's gonna be this distance right over here. So it's gonna be the absolute value of z cosine of theta. Then it's gonna be, well, this guy over there, so how much I have to walk upwards in the imaginary axis. Yeah, so that's just gonna be my absolute value of z sine of theta, and then multiplied by the imaginary unit. Yeah, so this is gonna be all equal nicely to the absolute value of z multiplied by cosine of theta multiplied by cosine of theta plus I multiplied by sine of theta. But wait, well, we've just proven that this guy right there is equal to e to the power of I times theta, and so we can rewrite this entire thing as just the module of z, so the absolute value of z times e to the power of I times theta. And so we can represent any complex number as just the length of the line segment connecting it with the origin multiplied by e to the power of I times the angle between the real axis and the line segment that connects it to the origin. Which is absolutely awesome, because now we can finally prove the Euler's identity, which is that e to the I pi is equal to -1. Yeah, so, well, we would like to see what -1, the number -1, actually is, and then write it in terms of this formula we've got right there. And so maybe I'll write this formula explicitly. It's gonna be z equal to e to the power of I times theta times the absolute value of z. Lovely. So now, well, I'm gonna mark my point -1 here in the complex plane. So I definitely gotta get myself a new camera anyway, guys. So, well, what is the distance of -1 from the origin? Well, that's just the absolute value of -1. That's just a 1. And then, well, we have to multiply by the component of e to the I multiplied by the angle between the real axis and the line segment that connects the origin and that number we are trying to write in that complex form, a polar form actually is called. So well, what is this angle right over there? Well, this is just 180 degrees, which is pi over, no, it's not pi over 2, it's just pi. It's pi, yeah. So we have to write pi there. And so after, well, getting rid of this 1 because we don't really care about it, we get that e to the pi multiplied by I is equal to -1, which is exactly what we wanted to prove from the very beginning. So once again, what did we do here in this problem? Well, we just kind of, first of all, nicely prove the Euler's formula using the Taylor series expansion for e to the x, sine of x, and a cosine of x. And then what we did is we derived a nice formula using which we can rewrite every single complex number in terms of an exponential and its absolute value, and then use that nice formula in order to write -1 as e to the power of I times pi, which was pretty much exactly what we're supposed to do in this problem. So, well, if you guys enjoyed this video, then, well, like and subscribe to my channel not to miss out on any future content I'm going to be posting. And actually, I'm posting every single day, so there is a lot of stuff to miss out on. So, well, consider it. And, well, see you next one. Bye.